Yeah, hello everyone. Good evening. Am I audible?
Good evening, sir. Yes.
Okay, great. So, how was the quiz 2 paper? Any feedback on quiz 2? No feedback.
So it was good. All the conceptual questions are there.
Okay, great.
Sir, if possible, please provide the solution.
Solution. Okay.
There are some questions which I have doubts.
Yeah, maybe you can post it on Discourse. We'll provide the solution there for those
Yeah, I
questions.
posted.
You already posted? Okay.
Yes, sir.
Yeah, so there was one question. The answer was con dot commit, right? And the function was there.
Yes, sir.
Yeah, so only con dot commit and that function was considered. Others, no, like con is not considered. Only con should be there, right? Based on the code. That's it. Okay, great. So yeah. So today we'll start
If
with the.
con dot commit only
Hmm,
is written, like if we don't call the function,
sorry.
if we won't call the function, just wrote con dot commit.
No, no. Still, it is not considered. Okay. So yeah, we'll start with the week 9. So only one session is there because tomorrow is the deadline for week 9. So we'll try to cover the what are the important concepts are there, so you can do your practice and graded assignments. Okay. Yeah. So yeah. So Mandipa will take the today's session. So yeah, over to you, Mandipa.
Good evening, everyone. So, I'll just share my screen and we'll start the discussion on week 9. Okay, is my screen visible?
Yes. Yes, ma'am.
Okay. So, in this week, we will basically learn about indexing, hashing, B trees, B plus trees, the data structures that are related to indexing. So, what is an index basically? Indexes are data structures that are used to increase the efficiency of searching records in a database. So this is an example of an index. Okay, so that here the table is the faculty table. Now we can have two different indexes on this table. Now here we have an index on the name attribute and here we have another index on phone attribute. But usually in one table we only have one primary index based on the primary key. So say for example take the this index that we have constructed on the name attribute. So here if you want to get the phone number for this person Pavitra Mitra, what we have to do is we will search in this index. Okay, so this index is sorted alphabetically. These are ordered indexes. We'll learn about that later. So here we can search the name easily. Here Pavitra Mitra, and you have to go to the corresponding record pointer, that is 6 here, and that will lead you to the original table. Okay, so in the original table you will find the same record pointer for this record. So number 6 is here, and you will find that tuple corresponding to Pavitra Mitra, and you can find the phone number here. So this makes searching much easier. Otherwise, if you want to directly search from this faculty table, you have to go through every record since you don't know no, which on which tuple, which row your desired phone number is present. So you have to linearly search. But with indexes, we can directly access that record. Similarly, if we take this index that we have constructed on the phone attribute, if we say want to search the name of the faculty who has the phone number 84772. So we'll search 84772 here. So we can see that the corresponding record pointer points to 7. So here's the 7th record in the original table, and you can see Prabir Kumar Biswas, that is the answer. So index makes searching a lot easier. Okay, so there are two, this is the, in any index file, this is how each index entry will look like. Okay, so it'll have a search key value and a corresponding record pointer. So the search key value is basically the value of the attribute on which you have constructed the index. For example, in this example, here name is the search key value. Okay, so based on this search key, the corresponding record pointer will point to the original table. So there are two basic kind of indices, ordered indices and hash indices. Uh, so we'll learn about ordered indices first. So in an ordered index, what happens is the index entries are stored in a sorted manner. Okay, like I showed you in this example, the index entries are alphabetically sorted, C A P R S. So like that, in ordered indices, the search key values are all stored in sorted manner. And now we'll learn about primary indexes and secondary indices. So these are all variations of ordered indices only. So what is a primary index? It is basically in a sequentially ordered file where the data is originally stored in a sequential manner. So if we form an index whose search key specifies the sequential order of the file, then that will be a primary index. Basically here the search key is the primary key. Like in this example, if we say that the phone number or the name, any of these are the primary key, then that will be a primary index. Say if name is the primary key here and we form this index based on name, the name attribute, then this will be a primary index because here the records are all present in sorted order. So basically in any primary index, the record has to be in sequentially sorted manner. Okay. This is also known as a clustering index. But it's not necessary that you always have to use the primary key for the search key values. You can use any attribute, but primary key is usually used. So we'll take an example of secondary index. First, let us take another example. Okay, so see, here's a dense index. So in dense index, what happens is we have respective record pointers for each of the records in the original table. Okay, so these are all of the records present in this table. So if we form an index based on this table, if it is a dense index, then the index file will have a record pointer for each separate tuple in the original table. Like here you can see 10101 points to this record 10101. Similarly, but there is another type of index which is known as the sparse index. Okay. So in sparse index, what happens? Only a few of the search key values are present. So basically, in a sparse index, we divide the original table into blocks based on the search key value. Like say this is a block starting from 10101 to 22222. So this is a block, and in a sparse index, what happens? You'll only point to the first record in the block. So here 10101 is the first record, so that is pointing to this. Now the next block starts from here 32343. Now we can form the blocks based on various parameters. Say we are dividing the block into 5 row units. So there are 1, 2, 3, 4, 5 records in every block. You can do it in any way. There can be any number of blocks that depends on how much space one block is consuming. So similarly, you just have to point to the first record in every block. Like 32343, this is the beginning of another block. Similarly, 76766 is the beginning of the third block. Like that. So next, here is an example for a secondary index. So secondary index is nothing here. You just have two indices for one single table. Like take an example here. For this table, we have two indices. Okay. So these are buckets that will have the record pointers, and the secondary index will point to the buckets. So the secondary index is basically not formed from a primary key attribute. We usually use other attributes other than the primary key. It is usually unordered, but here you can see that the first record 40,000. So we have done this on the salary attribute. Okay. So the search key values here are from the salary attributes. That is this one. So 40,000, it will be pointing to this bucket. and this bucket correspondingly points to this record Mozart music, because here the salary is 40,000. So it's nothing, you're just having an index on an index, so that is a secondary index. uh, Now, what are multi-level indices? So if the primary key does not fit in memory, then access becomes expensive, right? So what is the solution for that? We treat the primary index, okay, we keep it on a disk as a sequential file, that is, it is in sorted order, and we construct a sparse index on it. So that is basically multi-level indexing. You're constructing an index on an index itself. But the here what happens is that the cost overhead becomes very high, because once you update anything in the original file, you have to update it in the primary index, then again on the secondary index. That is, you have to update all levels of indices that are there. So this will obviously increase the cost overhead. So this is the structure of basically multi-level indexes. See, the original table is divided into blocks. So here we have constructed a sparse index. Okay. Here, see, the inner index is basically a sparse index. It is pointing to the first record of every block. You can see. Now
Um,
again,
um,
yeah,
Ma'am, is there any condition like the block should be in certain order, like ascending or descending, or they can be a random data between them in them?
that depends on the original table. Now, if the original table is in sequential order, then the blocks will be in ascending or descending, whatever order it is originally in.
But if we consider a denser space indexing, like in the example that you talk, the table is in ascending order
Yeah.
by certain keys. So is it mandatory for us for a table to be that? Like
In
can you scroll
Yes,
please?
continue.
Can you please scroll the space index example, please?
Okay, 1 second. This one?
Yeah, like in your ID thing, your that is record is in ascending order of ID itself,
Yes,
and
so that will depend upon the attribute that you are taking for the search key values. Like here, I'm taking this attribute, right? The
yes, ma'am.
ID column. So here, since 10101 is pointing to this block, no. So obviously, now if I take a value, say, wait, I'll show you. Okay, so now if I have a value, say 12134. Okay, if I have this value, so if it is not in a sorted order, then how will I understand which block it will belong in? Now, since it is 12134, so I know that it will belong. It is greater than this one, but less than this one. So it will be present in this block only.
So
So it has
before
to be in sorted order.
before applying this denser square indexing, we have to order our table that is table itself in ascending order before
And
applying.
that is why the tables, those are known as index sequential files, since they're already in sequential manner.
Okay, got it. Thanks.
Okay. Okay. So this is a multi-level
Excuse me,
index.
ma'am.
Yeah.
Excuse me, ma'am. Ma'am, why is data access faster in case of dense index
Since
rather than
see,
sparse?
see in sparse index, what happens here? See, now if I say want to access this record, okay, this 15151. What I have to do from the index, I will know that it is present between these two blocks, right? I know it is greater than this, but less than this value. So I will start searching here only, no, because I only have one record pointer that will point to the first record of every block. So then I have to linearly search until I find it. I have to compare with every record that's present before I reach this record. But in case of dense index, what happens that for each one of these records, I will have an entry in the index itself. Like
Ma'am, instead of linear search, as it is in ordered, that is,
you can,
then we can go
yeah,
binary search, no?
yeah, you can, but the time will always be greater than dense index, since you
Okay.
have to do an extra search in between. But in case of dense index, you can directly get the record pointer from the index itself.
Okay.
Okay.
Ma'am, in the dense index, like you said, all the pointers that you draw in the example are like from first value to the first record.
Yeah.
This linearity is there in complete this dense index example. Is it always maintained in this way, or they can be like uh, uh, first point might be uh,
Like you're saying that this record can be present here and this can be present here, right?
yeah, that thing.
That
No,
will
no,
have,
this sample, this pointers, like
yeah.
pointer from 1012 1011.
Yeah,
This
this will be obviously maintained. Whatever search key we are basing our index upon, that has to maintain. No? That's how we will know what record it is pointing to. If now suddenly I change this to this one, then that will not work. The search key has to be maintained. So for this search key, we have a certain record pointer that will point to this record only, which has this particular search key.
no, ma'am, you didn't get like in dense index as we have pointers to all the records in a
Yeah.
block. In that case, this records there is a possible. It does not matter whether record are in ascending order, descending order, or a random. As long as we are maintaining our index file in the ascending order, we can always go to the particular record in the same amount of time because of the pointer that we have.
Yes, of course. That
Yeah,
ordering won't matter as long as you are pointing to the right record
yeah. In the dense syntax, but in the
in
spare,
the dense index. In
in the
sparse,
spare.
you have to have it in the ordered manner, na? In sorted order. Otherwise, you won't understand what block a certain record would belong to.
Yeah, thanks.
Okay, so that's about multi-level index. So this, like I said, see, this is very important in case of indexing. That if a deleted record, there's a block, okay, which only has one record. So there's a block I'm constructing here. It would be better if I constructed a block here. I mean, where one block ends. Okay. So say here say this block is ending here. Okay. This is the last record for this block. So after this, if I construct another record, if I have another record here, so this is the beginning of a new block. Okay. But there is only one record in this new block. So for this, we'll have to have another search key, right? So since that is the first record in this block, say, okay, so this says 8000. Just take for an example that this record has a search key value of 8000. Now, this is creating a new block. So if I delete this record only, the whole block will be deleted, right? So if deleted record was the only record in the file with its particular search key value, then it has to be removed from the index also. Now see, if I delete this record 12121, right? If I delete this record, that doesn't mean that I don't have other records in this block. I still have this one, this one, this one. So this value, this 10101 value does not need to be deleted from the sparse index. But if I have only one record in a certain block and that is also deleted, then we have to delete the corresponding record in the sparse index also.
Ma'am,
Okay.
if we delete this 10101, then the block index needs to be changed.
Yeah, then the block index will point to the next record in that
Oh,
block. Then it will point to this one.
okay.
No, one thing like in each block, the in each sub block that a pointer our indexing file is uh, pointing to, there is some difference. Like in first block, there are certain less number of records, but in the next there are more. So, is there any process? If any, what do we consider? Like a pointer should be pointing to after leaving certain amount of blocks, or we just take a gap, means after this much amount of pointer records we will insert a pointer.
See, it's take for example, say I am saying that we have a block for all values that are between 1000 and 2000. Okay. So
Okay.
say in our record we have five values that fall between this range. But then for the next block I am taking all values that are from 2000 to 3000. So there can be more or less values than 5 in that block. So accordingly the block size will alter.
Okay, ma'am. So we decide a range, and according to that range, we create our index file.
Yeah, it depends on the metric on which we are making the sparse index.
Okay, so one of the bases is a range, and another is are there any another mode for this considering the space
It can
indexing?
be alphabetical also.
Okay, got it. Thanks.
Okay. So, okay. So next in the next module, we'll see
Ma'am, I'm not clear about one thing that which is faster, dense or sparse.
dense index is always faster than sparse. No, see in a
But
dense.
I'm not getting this point.
Okay, wait. I'll explain it once more.
Because, ma'am, in the sparse index, the value is like we have to search from for very less value, and in the dense index, we have to search for every value, for every key. And in
But you have
the
to
sparse
understand that
index, we have very less keys, so it should be faster in sparse.
no, sparse cannot be faster. See, in sparse, you are only pointing to the beginning of the block, right? So within the block, you again have to search. If it is not in a sorted order, say it is not in a sorted order, then you cannot even use binary search. You have to go linearly.
In the
So that
sparse,
will,
we can use binary now because it is sorted, and if we
in
use
this example,
two times binary, then we will log in plus log in. Yes. But in the dense, we have to use n.
okay, you are saying that you can use binary search, right? So what is the time complexity for binary search? Order of log n,
Yes.
right? So for searching any record, you at least have to have order of log n. If it is not the first record, then only it is a constant order. So otherwise, you have to do order of log n searches to reach your record using sparse index, right?
Yes, ma'am.
But if you are using dense index, then you can access any record in order of one constant time. That is
Ma'am,
always faster.
but for
But
that on indexing file we still have the complexity of log n. Na?
Yeah, the index file itself you have, but that is also present in the sparse index. So here also you have to see that which range your value is falling under. You don't know here. You can see only three values. There can be a much larger index file here. You still have to search which range your value is falling under. So if
ma'am,
I give,
how one
yeah,
like it should be n now because we have to search whole table.
yeah. So for the whole table, okay, say see here in this table, if you first have to find what range your say I want to search this, I have to know that what block it will be in, right? So I have to search accordingly in this index file. So here that will take order of n because I have to go sequentially to see. Okay. So but once I reach here, once I reach through the record pointer here, I again have to do another search. Now that can be binary search like you said, since the file is sorted. So that will take order of log n. But in dense, what do I have to do? I only have to check this file. Then it takes only constant time, right? So this extra time complexity, this won't occur in the case of dense index. Is that clear?
Ma'am, should not it also be the log n for this indexing file?
Yeah, if you are doing, if this file is also sorted, then it will also take login.
Ma'am, we are deciding by the by the range now. Like if we are deciding it by the range, then all obviously the first range will be smaller than the second, then the it will be smaller than the third. Like
Yeah, but then you have to go sequential order, no? Say there is 1, 3, 7, 9. There are more values in this index. That's now the next value starts with 9, 9,000. Then I
yeah,
have 10,000. So the index size keeps on increasing. So now if I want to search what range, say I want to search 5,000, what range this value falls in, I have to come here down sequentially. I have to search that. I don't have another option here. So if I want to do a binary search also, that too, it will take log n here. If I want to do a binary search, since it is sorted, you can do a binary search. That will also take log n time complexity, no? For
yeah.
this.
Yeah, that is one. Yeah,
So this will take log n. Now once I reach my record pointer here, I again have to search in that
yeah.
whole block for my record. So log n, log n. But in case of dense index, I only need log n. Then I have constant time since it is pointing to single record only. I don't have to search in this original file.
I
Yeah.
mean dense index how login uh,
See this one, right?
yes.
See this one. This is also in sorted order, see? One, two,
Yes.
three. So I can do a binary search here also. So this will only take log n.
Okay.
And
Got it.
here I have only order of 1 time complexity, right?
Okay.
So dense index is always better. Okay. Any more questions in this module?
Hello, ma'am.
Yeah.
Ma'am, we cannot use that dictionary thing here. Use as a key value for dense.
What dictionary?
Means in we will store the whole thing, the pointer and the as a key value pair, so that like
Yeah, we are doing that only. Na?
searching.
See, here's your search key and here's your record pointer. I haven't. It's
Yes,
not written in this example, but there is the format is always the same. You have a key and a record pointer. Here's your key first here, then you'll have a record pointer, and this record pointer will point to the original file.
yes, ma'am. And in sparse table,
The
like
format will
if you
always be the same.
dividing the yeah, thus if you dividing the sparse into a blocks, let's say the whole rows, let's say n, and if you divide it by let's say 10
Hmm.
into n by 10 blocks,
Hmm.
then also the time complexity to sort that key means that sparse table that will be like O of n by 10 and it will be equivalent to big of n, right?
Yeah, that is
Because
ON only.
10 is a constant. Yeah. So it will be like moving to ON. Yeah.
That is why I said na that dense index is always faster. The complexity will
That's
always
why
keep on
dense
increasing
index is
here.
faster.
Okay, so this is clear.
Ma'am, can you explain multi-level indexing again?
Yeah. Wait. So this is the structure for a multi-level index. See, this is a sparse index basically. See, we have divided the original file into block 0, block 1, say n blocks. Okay, this is block n, say. And we are constructing a sparse index on this, right? Now, this index, like the first record will point to the first record of this first block. Now, the second one points to the first record of the second block. Third one will point to the third block, like that. Now, see here, if we consider that there are like only two records in each block. Okay, that is why the second block here is, so this is where the block ends. So here, the first record is pointing to the first record of this block. It's like that. So you're basically you're forming a sparse index on the original table, and again you're forming another sparse index on the inner index itself. Okay. Sparse indexes, why do we use sparse index since dense index the speed is more? It's because you need to store less search key values. So there is a cost overhead for storage also, na? So we can decrease that by using sparse indices.
So, ma'am, if you can compare this dense and sparse indexes, then there is two trade-offs. One is like dense index gives us better a system for our record, but at
Yes.
the same time, the space to maintain the space index.
Yeah, the storage is much more in case of dense index since we're storing for every record.
Yeah,
But again, in case of sparse index, the timing is more, but the storage we need is less.
yeah. Ma'am, so this two aspects are there trade-off only.
Yeah. Yes.
Okay.
Ma'am, what is the need for multi-level indexing? It seems quite complicated.
No, multi-level indexing is needed. You will understand this concept better when I explain B trees and B plus trees. There you will see how multi-level index works and why it is important. It is basically needed so that we don't have to, store record pointers for every data in every level. We can only have it at the base level. I'll explain this when I explain B trees and B plus trees. You understand there. Okay. So in next module, we'll start with data structures that are used for indexing. So these are some basic data structures, right? All of you know about this linear search, binary search. So not even data structures; these are just algorithms for searching. This is a data structure, binary search tree. Now, you all probably know this that linear search takes order of n linear time since we have to go sequentially comparing every, entry in this array. And for binary search, what we have to do is we have to find the middle element, and every time we find the middle element, the array gets divided into two, right? So that is why we have log n time here, since every time the array is getting divided into two, like halves basically. And in binary search tree, what happens that we start searching at the root. If the value we're searching for, say we're searching for 10, so 10 is less than 25, so we go to the left subtree, and the right subtree we completely discard. Okay, so you see that every time we make a decision here that I want to move to the left subtree or I want to move to the right subtree, I am discarding the other subtree completely, which is why the time complexity in binary search tree is also order of log n. So here, if we want to find 10, we'll again come to 20. 10 is less than 20, so we'll search in the left subtree and you'll find the value here. So these are the time complexities. You can go through this list. Now what we are coming to trees. Okay. So what is a bad tree? So basically, in case of a bad tree, we have the time complexity of order n. Okay. So a BST now, a BST is a skewed binary search tree. Now, what is a skewed tree basically? A skewed tree is where for every node except the leaf nodes, we only have one child. Now, I'll give you an example for this. Wait. Okay. Say I want to form a tree where I'll insert these nodes. Okay. So I'll insert these 6 nodes. So if I want to form a tree, the first node is my 1, that is the root node. So now next is 2. 2 is greater than 1, so we'll go this side, right subtree. Similarly, 3 is greater than 2, this side, and it will go on until I have 6. So this is a skewed tree. Now this is the worst case possible for a BST. Now why is that? Because if I want to search any element, say I want to search 3, I have to start from the root and the height keeps on increasing, right? So this tree will, a skewed tree will have the maximum height. That is order of n. Here the height will be approximately order of n, since there will be n nodes. Okay, and say the worst case is when I want to find node 6, that is the last node, I have to go through the entire tree searching. So that is why this is the worst case time complexity. So that is a bad tree actually. A good tree structure is when the height is approximately equal to log n. So this can happen, like I said, a bad tree can happen when we are inserting keys in sorted order, like I just showed you. Okay. And in a good tree, what happens is that it is a balanced binary search tree. Now, this can happen when? When can we have a good tree? If the keys are purely entered in a random order. Okay. So then, if we enter the keys in a random order, then we have a possibility of getting a good tree. Or if the tree is explicitly balanced, like an AVL tree. So in AVL tree, what happens that uh, whenever we are entering nodes, we always make sure that, see, I'll give you an example of AVL here. You don't need that, but
What is AVL, madam?
okay, you don't need to know about AVL trees, but I'll just show you that why it is a height balanced tree. That is not in the scope of the syllabus, but see, in an AVL tree, what happens is that, say, if this is a tree, okay, so this cannot happen in case of an AVL tree because the height of the left subtree is 1, right? And that of the right subtree, the max height we get is 1, 2, 3. So the depth is 3 here. So what is the difference between the height of left subtree and the height of right subtree? Here we get a difference of approximately 2, right? So that cannot happen. Since it is a height balanced tree, so what we have to do is the height difference between the left subtree and right subtree can never exceed 1. It can never be greater than 1. Okay, that will never happen. The height always has to be a maximum difference of 1. So next, now these are some different types of data structures that you can go through: skip lists, play, randomized BS3. So AVL tree, I just told you what it is about. Randomized BST is where we are entering the nodes in random order, and what happens is any node, the possibility of any node being at the root is 1 by n always, because we are entering in random order.
Ma'am, for the evil tree, how does this? How is this self
Yeah,
balancing
yeah.
out?
So the balancing occurs, we actually use different types of rotations. Okay, there are LL rotations, LR rotations. You don't need to know about all of that in detail. Just know that there are rotations that are performed on these nodes to always make sure that the height of the left subtree and right subtree doesn't exceed 1. Okay.
Okay.
So you can go through these data structures. It's nothing, you just need to know what these are, just the definition. Like a skip list, it is a probabilistically built like layers of ordered linked lists. Splay is basically a binary search tree where the elements that we have accessed recently are easy to access again, like a cache memory, you can say, kind of. The elements that we're accessing recently, they are easy to access again. Okay. So now we'll learn about 2, 3, 4 trees. So here are some properties. These are very important for 2, 3, 4 trees. So in 2, 3, 4 trees, what happens is all leaves are at the same depth. So the height of all nodes, of all leaf nodes are same. That is, they are all present at the same level. Okay. Like if this is a 2, 3, 4 tree, then this cannot be a 2, 3, 4 tree because there is a leaf node in this level and there are leaf nodes in this level. It always has to be same. See, all leaves are at same level. And the complexity of search, insert and delete all will be log n. Since this is a height balance tree, you can see it is not skewed, it is not a bad tree, it's a good tree. So the searching algorithm will take order of log n time, like in case of normal BSTs, and for insert and delete you have just order of 1, that is constant time. You'll see that when we discuss the insertion. Okay, so the data is always kept in sorted order like normally we do in case of BST. Now there can be 3 types of nodes in these trees. Okay, now don't confuse this with normal binary tree. Okay, here the nodes can have more than one key values in them. So this, in case of 2, 3, 4 trees, what happens is that there is a 2 node, a 3 node and a 4 node. So a 2 node can have at most 2 children. That is, so this is a 2 node. Okay, it can have, I'm sorry, this is a 3 node. This is a 2 node. It can only have one key value and it can have 2 child pointers pointing to other nodes. And this is a 3 node. Okay. It can have 2 key values and it can point to 3 different nodes. So basically, if it is an n node, okay, if it is an n node, it can have n child pointers and n minus 1 search key values at max. It can have less than that. We'll see. Here, the same thing is discussed.
Ordered this ordered sequence. It
Sorry,
is this order. Yeah, please go ahead.
go
No,
ahead.
no. I'm asking like this. You said that all the data is in order. That is like same in sorted order. That is same like in that we had in BST. That
Yes,
yeah. Thanks.
it is a variation of BST, you can say, but here one node can have more than one key values in it. Okay.
Ma'am, and they are always balanced.
Yeah, they're always balanced. Otherwise, you can't have all the leaves at the same level. You'll see when we insert values, we'll learn how the balancing goes. So here you can see the 3 different types of nodes that I just told you. There's a 2 node, a 3 node, 4 node. Okay. So the searching is same as in BST. So time complexity will be order of log n here also. Now, let's.
For this 2, 3, 4 trees, like you said that search complexity is low again.
Yes.
Like on a one node, we have three values
Hmm.
at maximum. That is
Hmm.
three key values.
Hmm.
They are same ascending order.
Hmm.
But from the previous that is previous parent node, uh, uh, we have to perform log n operations to get to
Yes.
the sub node. Then we have to compare this three nodes that where our this this search values. Then we have to transfer downside. So it is not like
No,
that on.
I'll show you. It is a top-down approach, but if I show you a tree, you'll understand. Okay. First, let's learn the splitting, then I'll show you how to search and why the complexity is log n. Okay. So here. Let's start with splitting at root. So say the maximum node that we can have in a 2 3 4 tree is a 4 node, right, which can have 3 key values, sml here, and 4 child pointers. Okay, now what happens is, if we want to say enter another, if we want to say enter another value in this, say I want to enter p, so this will become the structure of the node, right? But this can't happen, we can only have 3 values, right? So what will happen, we have to split this node, and we will split always at the middle element. So this was our original node, we'll split at m. See, here the splitting is happening. So the m will become the root then. Okay, it will go one level higher. So when we construct a 2 3 4 tree, it is always a bottom up approach. And the s, since it is always in sorted order, so s's value will always be lesser than m, and it will come in the left subtree, I'm sorry. And l, it is in sorted order again, it will come in the right subtree. Now each of these can have, again, 2 child pointers at max, because these are now 2 nodes, right? It can have one key value, that is s and l, and 2 child pointers each. Let us see one uh, insertion example here. Let's start with this example. Okay, so the first node we are entering at the root is 10. This is a 2 node now. Next we enter 30. Okay, next we enter 30, this becomes a 3 node. So it has 2 search key values, 10 and 13, and it can have 3 child pointers. Doesn't have any pointers right now, but it can have. Okay, next is a 4 node. It becomes a 4 node when we enter 60. So it has now 3 search key values. Next we want to enter 20. So what will happen now? See, there are basically 2 strategies that we use. Okay, one is an early strategy, one is a late strategy. So in early strategy, what we do is, whenever we encounter a 4 node, we split it as soon as possible. Okay, even if we don't need to enter anything into that 4 node, even if we don't have to do any more insertion, we will split the 4 node. And another is the late strategy, where we only split the 4 node when we need to insert something in it. But we will follow the early strategy. Now you'll get to know why we do this. This is because if we don't do this, no, say we will keep this 4 node as what it is. So say there is a tree that becomes like this. There is a 4 node at the top. So there are 3 search key values, say a, b, c, and it will have another child pointer, say, which has which is again a 4 node. This will have, say, search key values p, q, r. Now say I have to enter a value s in this, so that will cause it to split, right? So this q then has to go one level above to this 4 node. Now again I have to perform another split here, since this is also a 4 node that's at its maximum capacity. So again I have to send this b to a higher level. So if we follow late strategy, we have to do multiple splits. We might have to do multiple splits when we encounter 4 nodes while insertion. But if we follow the early strategy, we will split the 4 node as soon as we encounter, like here. See, I got this after inserting 60. I got
Mama,
this
I
4 node.
didn't get what is the difference between early and late starts.
Nothing. It's just that in case of early strategy, as soon as we will encounter a 4 node, we will split that node in the middle. Okay. Like if we encounter this node, we will split it like we are doing here by the middle element. You will always have to split by the middle element. The middle element will go one level higher. And these become 10 and 60 become the 2 child pointers here. Okay. So in early strategy, we will split it even if we don't have to insert anything more into this node. But in case of late strategy, we will wait until we have to insert something. Only then we'll split a 4 node.
Okay, ma'am.
Okay. So now next we have to insert 20. So now I can enter 20 here. Since it is a 2 node, I am increasing this to be a 3 node, and I am entering 20 here. Next I have to enter 50. So 50 is greater than 30, it will go to the right subtree. I have a 2 node here, I will turn it into a 3 node and enter 50 here. Next I have to insert 40. So where will 40 go? 40 is greater than 30. It will come down here. Here I have 50 and 60 present. So 40 is less than both of them, so we will enter it into the leftmost position, right? And since it is in sorted order always. So now this becomes a 4 node. And since we are following the early strategy, we have to split this as soon as we encounter it. So now we'll split this node. So 50 will go one level higher. It will go to the root node. And this is a 2 node, so we can easily enter 50 here. And the left child of 50 will be 40 and right child will be 60. So now here you see this is a proper 3 node. Okay, this is a proper 3 node. It has 2 key values, 3 child pointers. You can see. Now next we have to enter 70. We can easily enter 70 here. It is greater than 30 and 50, so it will come to the left rightmost subtree where we have only 60, so we'll enter 70 here. Next, if we want to enter 80, now we enter 80 here and it becomes a 4 node. So early strategy will split it right here. So if we split 80, see, this 70 is the middle element. It will go up to the root, I'm sorry, and 60 becomes the left child, 80 becomes the right child. Now this root and these have become 4 nodes also. So we will split at the root now. Okay. So here 50 will go to the root node and 30 will become its left child, 70 will become its right child. Similarly, now we enter 100, and since we don't have any more insertions left, so we will not be splitting these two. Okay, since that's all the values we have. So any question in 2, 3, 4 trees insertion? Is it clear? Okay.
So, ma'am, you said that we have two strategies, that is early and later, when we
Yeah.
are inserting in this trees. So, if we don't have any, even if we are following the policy of first encounter and split, that is before one,
Hmm.
then even if we don't have any further insertion, we can just stop our process
Yeah,
at
you
the.
can stop it if there is no further insertions, but you can split it. I mean, there's no issue. You can do either.
Okay.
Okay. So deletion is not in the scope of your syllabus, but I'll tell you the basic thing about deletion is that we locate the node. Okay. Let's see in this example here. Say I want to delete 70. Okay. So what I'll do is I'll find the in-order successor of 70. So you know how to find in-order successor? It is basically the node to the right subtree, that is the smallest node of right subtree. Your in-order successor for any node will be the smallest node, smallest key value, let me say, smallest key value that is greater than the value that we want to delete. That is in this case 70. So here we'll search in the right subtree and the smallest value that is greater than 70 here is 80, right? So we can delete 70, this we can delete, and we will take this 80 above here. So we'll just replace it or swap it with the in-order successor. That is how you delete in 2, 3, 4 trees. Or if it is in a leaf, that now this is for internal nodes. Okay, now if it is in a leaf node, say I want to delete 20, you can just delete it like that. You don't have to perform anything, any other operations. You can just delete 20 because it won't change anything in the tree, right? Okay, so these are the advantages of using 2, 3, 4 trees. So like I said, all leaves are at the same depth, so it is a good tree. The height remains order of log n. Now the complexity of search, insert and delete. So insert and delete will again take constant time like you saw. But searching will obviously take order of log n. So all three will take basically order of log n. It's just constant time, so it doesn't matter. All data is kept in sorted order. And we can generalize this to larger nodes. Now this you will see in case of B trees and B plus trees. That is why we call them M-way trees. That is they can have order M. Okay, like here you have 2 nodes, 3 nodes. There we can have M nodes. That is like I said in the first slide. So if you have order n, then we can have, if a node has order n, then we can have n child pointers and n minus 1 key values in it. Okay, so we can generalize this. And it extends to external data structures. That is, we can use this type of trees for indexing. Okay, that is how we arrange the databases in our disks. These are data structures that are used.
Ma'am, two things here. Like I previously said that for a level we are having a log n, that is due to the height of the tree, the uh, time complexity. But still, at each node we have three key values,
Hmm.
at a maximum three values.
Yeah.
So whenever we are performing the first operation, we have log n time
Hmm.
complex. Then that after that we have this is at each sub level we have a maximum of this
Three
uh
values.
yeah, three values, so we need at least two comparisons to check.
So this is in sorted order, no? Here also you can do binary search. That will also take order of login.
Yeah, but for at the earlier stage also login.
Yeah. It will take
If,
login for searching on any level.
so you are talking about time complexity at one level, na, or complete free?
Complete tree. You can search any node in this tree. It will only take order of login.
Mm.
It won't change with the level. See, all of the nodes are in sorted order. So it will always be login. It is not a skewed tree, no, it is always height balanced. In case of height balanced trees, what did I tell you? See, if I want to search 15, okay, say I want to search 15. I'll start at the root. So I know 15 is less than 50. So I am discarding this right subtree completely at the first part only.
Yeah. Now I got this point. The second thing I want to ask, like you said, in the delete or insert operation, in the both processes, there is some either a node is either a node can be removed, or we
Yeah,
need to
but those will
create
take constant time only. That is why we are following the early strategy here, because if in case you want to insert and you have to perform multiple splits, then that will take more time. That is also a constant time. Splitting time is always constant. Node splitting time is always constant.
but even we have to split multiple at multiple levels.
Yes, but you are taking the insertion time only. You're not considering the splitting time here. How much time do you need to insert a node?
After
You'll
finding
only
one,
you'll only have constant time, order of one time.
yeah.
You have to search where you want to insert, and then you have constant time. The splitting time, these are all constant times. You cannot find the complexity here.
So we are considering only this. After we have searched the correct road, then
Yeah,
we
you
are.
can directly enter or you have to split and enter, but that will also take constant time. Okay.
Good evening, Manideepa. This is Naren. Nice meeting you. See, I have doubt in that order of n we were talking.
Okay.
So, at height of one, how many uh, keys we can have maximum?
At one height, so you can have a four node
Height
here.
of 12.
Yeah.
4 plus 4, we can have 8, isn't it?
Eight, how? You can maximum, you have a four node. So that will have three search key values.
So, 12 you can have
No, no, root node will only be one node, na?
always.
Yes, root only you will have one node in the root. You can't have more than one node in the root. Then how will you start your search?
Okay. So, root node will be 1 and the next below that will be
Yeah,
3.
see, a root node can have at least two child pointers. Okay. I was going to discuss this in B trees, but since you're asking now, so a root node can at least have two child pointers.
At least or at most?
At least. If
At
my
least.
root if my root now becomes a three node, like it became here. Here. You saw this part, right? This is also a root, but this is now a four node and it has four child pointers.
Yeah, 4 child pointers. Each child can have 3 keys, correct? No?
Each child can have at max three keys.
3. So, 4 threes are 12 keys we can have.
Not on one level. This is a separate level, the child is on a different level.
That's what in child, at child level,
Yeah.
at the last leaf node level, how
Yeah, you
many
can have
keys we
at
can?
max 12 keys. Yeah.
12 keys are there. And height is h.
Yes.
And 12 keys plus 3 keys in the root node. So, that's about 15 keys.
That's the worst case. Yes.
You
I mean,
know,
that is the max you can have.
we are talking about max only. Worst case, there are 15 keys are available.
Yes.
So now to search any key, why we require so many? I mean, whatever key is there, only one H is there. No, one height you can always come there and you can get it. No, three. You require login for that.
Yeah, I require always login for it. Whenever you are having a tree, that is, like I said, if you say want to search 15, every time you are dividing, na, every time you divide, the height becomes login because you're like completely like
No,
ignoring the rest of the
height
tree.
is not login actually. Your complexity is login. Height is only one. H is 1 year.
In case of any good tree, the height is always login.
No,
I showed that in the beginning only.
no, that's okay. But when we came to 2, 3, 4 trees, and particularly this particular tree which we are discussing, there are 15 keys are there,
Yep.
and the height will be one or login.
There can be more height, no?
No,
I can always increase here.
no,
I can always split here. See, the height is increasing here.
I am not. We are not asking about that, Manidita. There are three keys in the root node,
Yeah. Yeah, so
and
here the height is 1.
yes, so height is one, and
Yeah,
keys
in
are
this case.
15.
Yes.
So n is 15.
Yeah.
So log n will be for 15. It will be 3.
Hmm.
But you are saying h is 1 only. No, here
That is for time complexity.
height
Wait,
and type complexity both are different. No.
wait. Just give me 1 minute. See, height is always, it will be order of login.
That
In
is what
case
I'm
of any
questioning.
binary search tree or related data structure is always like this.
That is what I am questioning actually. Why
Yeah.
it is so? I am not able to understand. Height, how can it be log n? Because when n equal to 15, what is the
Hmm.
height of 2, 3, 4?
No,
Uh,
you are not doing it right. See, we are not considering the search keys. N is the number of nodes. You are adding the search keys. So it is not 15.
n
Okay.
is node.
Yeah. N is node. N is not search key. See,
Okay,
in
so
this case,
5
here is
nodes are
5.
there.
Okay.
So 5 nodes log n means log of 5 will be 2.
Yeah. So that won't be exactly 2. You have to take the floor value.
Okay, 2 to the 4. It is more than 4. So I am taking it as 2 only.
So this is one level. This is one level. Two levels.
Oh, here height is not as the
This
measured
is
as the hs.
actually, yeah. See, this is
Height
level
is
1. This
measured
is
as
level
h.
2. No, height and depth are different things. You're talking about depth. This is depth. This is height 1. That is height level 1. This is height level 2. And this is depth. The depth is 1, but the height is log n.
No, no, we have to mention the root node is height of 1 then.
Yeah, it is always at height of 1. There is no height 0,
It
right?
has to be mentioned, madam. In PDSA,
Okay,
there is a
okay.
problem. No,
Okay,
we
sure.
can,
If you
if
want
there
that,
is
I
no.
can.
No, I am just asking because it is given the notes and even activity 9.5 it is there.
Okay. Okay, you want me to check that?
No, not only 9, not 9.5. Where we are talking about 1, 2, 3 is 9.4.
Okay, is this clear here?
No, I am still not able to understand that.
See, okay, I'll tell you one more time. Okay. Here are 5 nodes are here in this tree, right? One, 2, 3, 4, 5. You talk about nodes. Okay, n is not the total number of keys present in each node. It is the number of nodes only. This whole is one node. Okay,
Okay.
this is one node. So there are 5 nodes. So height is log n, that is log of 5. So that is approximately 2, right? So you
More
have
than
two.
2, so we have to take it is 2 plus 2 point something only will give log 5.
Yeah, but you can take the floor value here.
We are taking floor value, not the roof value,
No, no, no,
ceiling value. Okay.
no. So you
Okay.
have height 1 here, height 2 here. And this is your depth. Okay, height and depth are different.
No, I've never heard of any depth in
Now
both.
depth concept is there in data structures trees. You can search it. So depth is basically height plus 1.
Height plus
I'm
1.
sorry, height minus 1. I'm sorry. Depth is height
Okay.
minus 1. You can Google it also. Depth concept is there in data structures. You can use it.
In our course, we have not seen it. We'll forget about that.
Okay.
So, n, wherever you are mentioning n, it is only nodes.
It is nodes only. It is not the search key values.
Even when we are talking about the indices, index, no, hashing or
Mm-hmm.
whatever, there also n is nodes only, or
Yeah, yeah.
it's,
N is always nodes.
oh, it's only
Search key values. See, in case of binary tree, what do we have, right? This is a node. So we have one here, say 4 here. So these are nodes, right? These are all nodes. Similarly, we just have more than one key values in there, but it is a node. The whole thing is a node.
okay. Okay. Anyhow, with this new insight, I will try to
Yeah, that
study
way.
about.
Always remember that in case of these trees, height is always log n because it is a height balanced tree. So the best case will always be there. Log n is the best case.
Best case or worst case?
Worst case is order of n. That will never happen in case of 2, 3, 4 trees. Now we are always splitting at every level.
So best case and worst case both are same for 2, 3, 4.
Yes, it will always be log n only.
1, 2, 3, 4, 5, 6. But in the same slide you're showing, there are 6 nodes are there, but the height is becoming 3, no?
Yeah.
How?
So you
6
take
nodes also, it will be.
seven nodes. 7 nodes. 1, 2, 3, 4, 5, 6, 7. So it is
Okay.
very much close to 3. So then you will take 3 height.
Manideepa, you have to be very correct. Whether floor value or ceiling value. Near and far is difference. Should I take floor value or ceiling value?
You'll take the closest value.
I okay.
Okay, okay. If you have a confusion in this, I can discuss this and come back to you on the next
Yeah,
session.
please do that because there
Okay.
is nothing like nearest and all. Either it has to be floor or it has to be ceiling.
Madam, for this 7 notes, the height is only 2 na, sir. 2 na, madam.
No, here the height is 3.
3.
No. The node is at 0 level na.
Okay, give me 5 minutes, please. I'll get back to you.
When the node is taken at 0 level, the next level
Yeah,
is
yeah,
taken,
yeah. Just give me
taken
5
one.
minutes.
Sure.
Next level is taken 1 and another next level
Dinesh
is
Murthy
taken
sir,
2.
5 நிமிஷம் வேணுமா இருங்க. Okay.
Hello?
Yes, ma'am.
Okay. So is it okay if I answer this in the next session? I have to discuss
Sure. You can.
because I don't want to
Yes.
give you any wrong information. So I'll
Sure.
discuss this and I'll get back to you.
Sure. So, to know what are the other, what is the program for today? You are going to discuss all this theory part,
We will
or
again discuss it on Saturday only.
are we going to take any practice assignment questions or
Yeah, I will take
question?
practice assignment questions in this one only if you
Okay.
have time.
Yeah, sure.
Otherwise, we'll discuss it in next session.
Okay, because tomorrow is the last date for graded assignment.
Okay, then I'll try to cover some of the practice questions in this session only.
Yeah, practice assignment questions. Thank you, madam.
Okay, and this I will get back to you next
Sure.
session.
Thank you.
Okay.
Ma'am, can you just show this thing like without if we are directly performing an insertion, then
Hmm.
how is our time complexity order n that you said?
Order n.
Constant order.
It is only constant order. Now see, if you want to insert in leaf node, what do you have? You don't have to do anything else. You're just inserting in a node. Now that
But
will
but
obviously be constant.
ma'am, but before that we have to find the leaf node, no?
So that is log n, na? So total complexity is always log n. I told you that insert, search, delete all have order of log n
Okay,
totally.
got it, ma'am.
But for the insert operation itself, you only have constant time, or delete also.
Okay, for whatever we are doing, we have to perform this
Yeah,
for.
since even if you want to insert or you want to delete, you have to search that node first where your desired value is present.
Yeah, ma'am.
So that will take order of log n, plus you add on constant time for insertion or deletion. So it will basically be order of log n only.
Yeah, thanks, ma'am.
Okay. Okay, so we discussed advantages. Now these are some of the important things. Okay. Now here you can get numerical questions from here. So for any internal node, we can have 2 to 4 children links, right? I said two node, 3 node, 4 nodes. So you can have 2 to 4 children links for an internal node. Leaf node can have 1 to 3 items. Any node can have basically, since at max you can have a 4 node and it can have 3 search key values. Generalizes to easily to larger nodes, like I said, for B3 and B plus 3 you'll see that. Now since all the leaves are at same level, so you will have same length of path from root to leaf for every leaf node. And each node that is not a root or a leaf has between, now this is important, has between n by 2 and n children. Now an internal node must at all points have at least n by 2 children. Okay, here n is the order of the node, so if I have a 4 node, it must have at least 2 search key values. I'm sorry, children. It must have at least 2 children, that is 4 by 2, n by 2. Okay, and a leaf node has between n minus 1 by 2, and you have to take the seal value for this, and n minus 1 values. These you have to remember on numericals. Now there are some special cases. If the root is not a leaf, now in a tree it can happen, right, that it only has one node, say 10, 11, 12. Now this is the root, this is the leaf itself. So if that is not the case, then it at least has to have 2 children. And if this is the case, then obviously it won't have any other children, right? This is the root node, this is the leaf node. Now it can have between 0 and n minus 1 values. These are special cases.
Ma'am, the
Now
root node can have one or two elements, no, or just one.
it can have one element, it can have 2 elements,
Yeah, but
three
not
elements.
also. Actually, we have to perform the split.
Yeah, in early strategy you will perform the split if you encounter a 4 node.
No, I just wanted to clarify that point. See, basically, when your data set is containing only 3 elements, so there is no requirement of a split. Only when your
If you
instruction,
have to insert,
only when an instruction comes that one more, okay, 13 has to be inserted, then it will check early strategy. What it does is it will check the root node. If it is 3, it will immediately split it. In the other strategy, what it does, even though the 3 is there, it will go down, and wherever it has to insert that particular node, if it is having 3 keys, at that particular point only, it will split the node. So that is
yes,
the
yes.
difference. So as soon as the the root node contains 3 keys, there is no requirement for splitting. Just one correction. Because the
Okay.
same question he asked, no, Ankit asked, when 10, 11, 12 are there, we are supposed to
If
split.
you don't have any further if you don't have any further insertions in this, you can keep it like this. There is no
Yes,
issue.
yes, that is a clarification.
Yeah, means root can have n nodes itself if that n is free.
If it is a node of n order, then it can have n minus 1 key values in this and n children pointers. Like this is a 4 node, this has 3 key values, and it can have 4 child pointers in this.
Yeah, got it.
4 child pointers or 4 child nodes?
Pointer means nodes, right? They're pointing to child nodes, so they can have 4 pointers.
How many nodes, how many pointers will the host, when rather root node will contain?
That depends on the order of the root node.
In our 2, 3, 4 condition?
If your the root node at least have to have 2 child pointers.
And maximum is?
Maximum is 4, obviously, since your root can become a 4 node. So in that case, you'll have 4 child pointers.
Oh, okay.
Like you saw in the in the one you asked where we were discussing the height, right? In
Yes.
this case, see, the root has 4 child
No,
pointers. This is the
pointers
maximum we
and
can have.
the index pointers and pointers are different or same?
If you have a problem with the pointer term, you can use children. You can say that the root can have
No,
four
no, there
children.
is one question in the other activity. So it comes, no, like
What is the
size of
question?
size of child pointer is to some size they are given 12 bytes, 15 bytes, something like that.
Yeah,
So,
yeah. That is in
so
case of B trees or B plus trees, I think.
in the one only those trees will have pointers. Even in 2, 3, 4, it will not happen.
You have
Pointers will be
pointers, but
at,
we are not showing the pointers here separately. But in case of B trees and B plus trees, I'll show you where the record pointers are stored, where the child pointers are stored. You'll see that there.
okay, okay. So when we come there, then more clarity will be there, madam.
Yeah,
Thank
yeah.
you.
This is just the base for B trees and B plus trees.
Okay, thank you.
See here, we explored 2, 3, 4 trees in depth as a precursor to B and B plus trees. Okay,
Okay.
okay. Now in this lecture, we will learn about B trees and B plus trees. Okay, so it's better to start with examples, but I'll tell you what a B plus tree is first. Okay. So now on, whatever we learn, there will be an extension of that 2, 3, 4 tree only. So what is a B plus tree? Here you'll learn the properties. It is a balanced binary search tree. I'm sorry. Balanced binary search tree follows multi-level index. So someone was asking now, what is the utility of multi-level index? You will see here has the leaf nodes denoting actual data pointers. Okay, this is very important. So in B plus tree, what happens is the leaf nodes contain the data pointers, the actual record pointers to the disk. Okay, say this will point to the disk, but the internal nodes, they don't do that. They only point to the leaf nodes. So the leaf nodes in B plus trees will contain all of the nodes of the previous levels also. You'll see that in an example. Okay, ensures that all leaf nodes remain at same height. This is constant. This property will be followed everywhere. So here the leaf nodes will be linked using a linked list. So the leaf nodes will be linked amongst each other also, like some simple linked list. I'll show you the node structure for B plus trees. And here we can have random access as well as sequential access. Since we are following a linked list patterns, we can always have sequential access, and random access is obviously available. Okay.
Remember, for the random access, we are accessing from a level up high to a sub block, that is a sub node. But after that, this like DEF, this node, that at a level that is at height at the base. Is it
Hmm.
a list itself, or is it as a linked list, as an
It is a
arrow?
linked list.
I
See
mean, so
here,
all,
the every leaf node will contain a pointer to the next leaf node
but
at the
with
end.
but within the node itself.
Within
Uh,
the node itself, it's normal. No, there is no link between the search key values. Okay.
okay, that's just like an array.
Yeah, but it will always be sorted.
Okay, got it.
Okay. So here are the properties for internal nodes in B plus trees. Okay. At least n by 2 child pointers, just like the previous one, except the root node. So the root node can have at least 2 child pointers. It has to have at least 2. And at most n pointers. So for a node of order n, we'll have n at most n child pointers. In case of leaf node, we'll have n by 2 record pointers at least, and n by 2 key values. These are minimum, and at most n record pointers and n key values. I'm sorry, this
Madam,
should
now these
be.
child pointers and record pointers are different, no? Or same?
No, record pointers are different. Record pointers are basically pointing to. Record
Record
pointers will only be present at the leaf. Okay, they're
leaf.
pointing to the disk itself where the data is stored.
Only
Child
for.
pointers are these. These are child pointers.
Okay,
These
okay,
ones.
correct. Okay, okay. Okay, madam, thank you.
Okay. So we'll see how to search in B plus trees. So say I want to search 55 in this tree. Okay. So this is the root node. So we have 25. So 55 is greater than that. We'll go to the right side. We have 50. Then we'll again go to the right side, and we have 75. So we know that 55 is present somewhere between 50 and 75. So we will go to this child pointer, which is at the middle. Okay, this will point us to the left node where 55 is present. Now here you have to search sequentially. See, 50, you will first reach 50, then you will go to 55, and here you will complete your search. Now for insertion, I'll show you in a different example. It's a little bit less complicated. Okay, is it visible?
Ma'am, only the main slide itself, that is 9.3.
Okay, this is not visible. Okay, give me a minute. Okay, now it's visible.
Yes, ma'am.
Okay, hold on. I'll start with B plus trees. Okay, so this is the node structure of B plus trees. Okay, see, for any internal node, this will be the node. Wait, consider the internal node of node structure of a p order B plus tree having q less than equal to p block pointers. Okay, so this is the node. Now these are the search key values. Okay, k1, ki minus 1, kq minus 1. These are the search key values, and for each value in a B plus tree, you'll have a record point. You'll have a child pointer. So this is the child pointer for k1. Okay, so this child pointer will point to the subtree that will contain all values that are less than k1. And if there is any value that is greater than k1 or equal to k1, it will come in a separate pointer to the right side of k1. Here that is not drawn, but we'll see that in an example. Similarly, here you can see all of these works in the same way. Now this is the
Ma'am,
structure.
does like we were having earlier capping of a maximum three entries in the this node itself. So in that in B plus tree, are we not considering that? Like like you have
Uh,
represented after this K1 dot dot K then.
no, there are more nodes here. Okay, so there is a PB2, then K2,
Okay,
PB3,
so
K3.
at each node we can have more than three also in B plus tree.
Yeah, that is just a generalization. Now here you can have n values. Okay, say I
Okay.
have written P order B plus tree, so
Okay,
it
ma'am.
can be of any order.
Uh, okay.
Okay, so this is now, see, the internal node structure and leaf node structures are different in case of B plus tree. Okay, so this is a leaf node structure. In leaf node, what you'll have is you'll have each key value and a record pointer for that key value. So leaf nodes will be pointing to the disk itself. So you have K1 PR1. This is a record pointer for K1, and then record pointer for K2. And at the end, you'll have another pointer that will be pointing to the next leaf node. So we are forming the linked list like that. Okay. Now we will see how we construct a four order B plus tree. Now these are the values what we have to insert. Okay. So it is a four order B plus tree. So we can have at most three key values in one node and four child pointers, right? Like I said, if it is n order, you can have n child pointers and n minus 1 key values in a node. So at first we'll enter 1, 4, 7. We have no problem. We are entering them in sorted order. But now we want to enter 10. So we cannot enter here, right? The maximum three values have been reached. So now we have to split this. See. So we are splitting. So in case of B plus tree, what happens is the splitting is a little different. I'll show you. Okay. So this is my node. It's visible?
Yes, ma'am.
Okay. So this is my node, right? Now I want to enter 10. So before splitting, we have to consider it like this. Okay, we have to consider that we have already inserted 10. Then only we can split. So this will be how it's done. Okay. So now we will split in the middle, but there can be two middle elements, 4 and 7, right? but we are taking this, the right element will be taken in this case. Okay, if there is say a 5 order tree, then you can have 4 values. Where will you split? You will take the right value. So this is a right bias tree. You can also construct a left bias tree where you will split at the left node, the middle one. So there here in the middle you have two nodes, so you can either take the left one or the right one. So I'm taking the right one here. So we'll split at 7. So 7 will go here. To the left of 7 you'll have all of the values that are less than 7, that is 1 and 4 here. Now to the right of 7 you have to enter 7 itself. Okay, 7 itself, and then you'll enter 10. Now in B plus tree I told you now, all of the levels that are above the leaves, all of the search key values that are present in all of the non-leaf levels, all of the search keys have to be present in the leaf nodes, because the leaf nodes are the only ones with record pointers. Otherwise you only have child pointers. These are not pointing to the disk. So if you want to find 7 in the disk itself, you have to find it from the leaf. So the leaf will have a record pointer. So 7 must be present in the leaf. Okay.
Ma'am, I'm not getting this. Can you please explain a record pointer and child pointer again?
Yeah, sure. See, you understood the split, right?
Yeah. And
Okay.
is it necessary that B plus tree is always right biased?
No, it's not necessary, but we will be following this only in this course. We will be following right bias trees.
Okay.
Okay. So here 7, the left of 7, the child pointer to the left of 7 is pointing to this node, right? So this is a child pointer. Okay, it is not pointing to the records in the disk for the search key value 1 and 4. It is just pointing to this node itself. This is a child node of 7, right? Of this node. This is a child node. So it's a child pointer. But when you come to the leaf node here and you have the search key value 4, so this 4 will have a record pointer to the disk here. Okay. So that is the actual value that is stored in the disk. Only leaf nodes will have will have record pointers. All other nodes, internal nodes, will only have child pointers. Is it clear?
Yes.
Okay. So that is how they're splitting here. So now you understand. 7 is stored here. It's a leaf node. So there is this. We're forming a linked list. Next, we want to enter 17. So 17 is greater than 7. We'll insert it here. And there's no problem. It is a 4 order tree. So we can enter 3 values, right? Next, we want to enter 21. Now we'll again face the same problem. So we want to enter say 21 here. So we'll have to split. We'll again take 17 since it is right biased, and we'll take it to the root. So the root will now become 7 and 17. The root will now have two elements in it. Okay. And 7 and 10 come to the right, and 17 itself has to be present in the leaf node. So 17 and 21 will come to the right of 17. Next, you want to enter 31. Similarly, you can just enter all of these values. Like 31 will come here. Again, we want to enter 25. 25, if we enter, we have to split this. So now 25 goes to the root. Next, we have to enter 19. Okay, so 19 will be entered in this node. So there's no problem. We can have this since it's a 4 order tree. Next, we are entering 20. Okay. So again, a split will occur. So now this time what will happen? We have to split in this node, right? So if I split here, now 20 will go above. Now this node will also have to be split since this node also can't have more than 3 values. So now 20 will become your root node. And to the left side you'll have 7 and 17, and to the right side you'll have 25 and the corresponding left and right subtrees. So that's basically B plus tree. Any questions from here? Okay. So now I'll start B tree. Okay. So now this is the internal node structure of a P ordered B tree. Okay. So B tree is basically a more compact version of a B plus tree. Here we don't have any duplicate nodes. In B plus tree we are having duplicates. Now at every stage we had a duplicate value in the leaf node. So in case of B tree we don't have any duplicates. We only stored each value once. So what do you think will be the change in this case? In case of child and record pointers, what do you think will be a change in case of B tree
My
from
first
B
thing,
plus tree?
the child nodes cannot be interlinked because the information or order will not be preserved.
Yes,
Missing the first value.
exactly. There will be no linked list type in leaf nodes. And what about the internal nodes? You can see the structure. You can tell me from here.
Internal node does not have any capping of like three nodes or something that we were having there.
No, see, the main thing is that in case of B tree, all of the internal nodes will have the record pointers. Since you don't have any duplicates in the list, right? So each search key has to have its own record pointer. Like K1 will have its record pointer PR1. So all of these nodes will be pointing to the disk itself, not just the leaf nodes like in case of B plus tree. Here all nodes point to the disk. Okay, so it's more compact actually.
Uh,
Now, yes. You want to say something?
Ma'am, if it is directly pointing to our this record itself, then what is the use of like having a child node?
That is how you're sorting, no? You can't have all of the nodes in one level only.
Yeah, we cannot have, but does our child node also have a pointer to the record?
Yeah, every node will have a record pointer here.
Okay, okay. Check out.
Every
Ma'am,
node will have a
one
record
and
pointer.
one thing more, like in B plus example, you had only three values in the node itself at a maximum. After that, we perform a split. As soon
That
as
was
we
a four order. That was four order B plus tree. Okay, we can have any
okay,
order.
okay, just we have to decide that thing that how much number of nodes are accumulated at a node, based on the order of the tree itself.
Yes, yes. If it is an n order tree, you can have at most n child pointers and n minus one key values.
Yeah. Okay, got it, ma'am.
Okay, so here every node will have a record pointer. So now we'll construct a three order B tree. So how many child pointers and how many search key values will be there?
Three child values, two search.
Two search keys, two key values, n minus one. So three child pointers and two key values for each node at max. So this is a three order B tree. Let's construct this. Okay. So first we are entering 20. So first we're entering 20, then 50. So now this node has reached its maximum capacity. So now if we want to enter 40, we have to split this, right? So we'll split in the middle. 40 will go above to the root. Okay. Next we have to enter 80. We can enter 80 to the right side of 40, and it is greater than 50 also. So to the right side, rightmost 80. Now if we want to enter 90, we again have to split. We'll send 80 to the root node. See, 80 will go to the root. 50 in the middle, since it is less than 80 and greater than 40, and 90 to the rightmost side. Now if you want to enter 10, similarly leftmost, then 30, you again have to split this node. 20 goes above. You can enter the value similarly. Okay, is there a do you need me to explain this whole thing, yeah, or you'll understand by yourself?
Ma'am, can you share the link in the chat box itself, or this
For
slide?
this presentation, okay, okay, I'll share it. Okay, so that's how B trees are different than B plus trees. Now we'll take some questions. Okay, since someone wanted me to discuss some practice questions. So, okay, let's take this question, for example. So consider there is a B tree of order 17. So what are the minimum number of child pointers and keys that can be placed in a non-root node? Tell me. Minimum number of child pointers and keys, both minimum. Anyone?
N by 2, that will be 9.
Take the seal value, okay?
Yes. So that will be 9. The minimum number of child pointers, number of keys,
Yeah, minimum number of child
child
pointers.
pointers will be
Yes,
9.
9. And keys?
9.
Okay, keys, that is a
Keys can be
formula, okay?
17, no? You can have
No, keys,
all
that is, no,
17
minimum.
can be there.
I'm
So
saying
minimum.
minimum. Yeah.
Minimum keys is
No, there is a
very close to,
formula.
no?
So I'll tell you the
16.
formula. The formula
N
is
minus 1 by 2. Right?
Yes,
N minus.
exactly. So 8.
8.
So this is the answer. Minimum number of child node pointers is 9. Keys is 8. So I'll go to the practice questions itself. So
Ma'am,
this is the practice. Yeah.
ma'am, by order we means here like, the number of nodes that we have.
Sorry, can you repeat?
Ma'am, by order 17, what does we mean?
It means the value of n. That is n is equal
Okay,
to 17. So this tree, each node
okay,
can have at max 17 child pointers and 16
uh,
search
Ma'am,
key values.
okay.
ma'am, can you give an example like with order 3 how the minimum can be calculated with an example like diagram
No, no,
example?
there is no such thing that the minimum can be calculated. It is a rule that it has to have at least n minus 1 by 2 child keys in each non-root node. Okay, this is a rule. It has to, otherwise you cannot extend, otherwise you cannot form another node. You have to first have, like, each node must first have n minus 1 by 2 values. Only then you can form another node or split.
Ma'am, for this idea, the node I get, but what about the
See, if you don't have at least n minus 1 by 2 values, then what is the point of doing this height balance data structure thing? No, then the height will keep on increasing. We will be using a lot, wasting a lot of space. Say I can enter at least 16 search key values here, right? It is of order 17. So if I don't even enter 8 and I keep on entering values in another node, so a lot of space is being wasted. You have to at least fill half of each node before moving on to the next.
Uh, Ma'am, in the previous example, uh, where the order is 3,
Yeah.
yes.
Here.
Here, how, what is the minimum keys?
So order is 3, so you calculate 3 minus 1 by 2, that is 1. So each node at least has 1, right? See, at least has 1 search key value. Can't have 0 here. So if
Ma'am,
it is a 4 or,
ma'am,
yeah,
but if we consider like when we were considering constructing this, at some point 2 and 50 node did not have any child node. Like you can
yeah,
scroll up, you can scroll
okay,
up.
okay.
At that instant, if we were having only 2 and 50 insertion,
So these are now leaf nodes. These are becoming leaves, no? I'm talking about internal nodes.
yeah, yeah,
Leaf
yeah.
nodes can have 0 child pointers. That's fine, and that's why they're leaves.
Okay.
Okay. So I'll take the practice questions. So we did this question. Now, okay, take this one. There's a non-empty B plus tree of order 17. What are the maximum and minimum number of keys that can be placed in the root node?
17 means 16 keys can be there maximum.
Yes.
Uh,
Minimum
And what is,
one.
1 is also okay. So it should be
yes,
16
1.
and 1.
It is for any root node you can have minimum of 1 keys. I said that any root node can have a minimum of 2 child pointers, so basically 1 key. So 16 and 1, that will be the answer. Okay. Uh, okay.
This one can you do? 3?
Yeah, yeah. You want me to solve this?
Yes, madam.
Okay. Okay. This is the question. So we have total number of records is 100,000, right? Now each disk block can contain 10 records. That is 10 records per block. Okay. So how many blocks will be required to store all of these records? Total blocks required So that will be 10 to the power 4,
100,000.
right? That is
Yes.
this divided by 10. So 10 to the power 4 blocks. Now the total space, okay. See here it is written. Total space required to store the file is 100 MBs. So from here we can say that 10 to the power 4 blocks store 100 MB data. Okay, this is clear. So how much will one block store? I don't have a calculator here. Some of you have to help me. So this is we'll convert it into bytes by 10 to the power 4. How much is this? Can anyone calculate? Is anyone calculating this? Okay, fine. We'll calculate that later. I'll just tell you the concept of how to solve this. So we consider a primary index constructor on the data file. The key, okay. So we are forming an index on this file now. So the key field is 30 bytes and the pointer field is 10 bytes. So for each entry in the index, each index entry will have 30 plus 10, that is 40 bytes. This is okay? This is for each index
Ma'am,
entry.
why 2 raised to power 20? It's, I think 2 raised to power 10 MB is there.
KB is 2 raised to power 10, MB
Okay.
is 20, GB is 30.
You can
Okay.
write the answer 104857.
104857 point something,
0.6.
point 6. Okay. Okay. So this is that this many blocks require this. So one block will require this many bytes. Okay. So each index entry, now we are forming a sparse index on this file. So each index entry has 40 bytes. See, here key field is 30 bytes and record pointer is 10 bytes, so 40 bytes. Now how many blocks are required to store this index? Okay. So we have 40 bytes size. Now in a sparse index, what do? We point to the first record of every block. How many blocks do we have here? 10 to the power 4. So how many index entries will have?
40 byte time 10.
40 into 10 to power 4.
So total index is, so 4 into 10 to the power 5. Okay. This many index entries I'll have.
Yes, sir.
So how many blocks are required to store the index? Okay. So the total size of this is this many bytes. Okay. So one block can store this many bytes. So how many blocks will we need to store this one? Just do the division
Division.
here by 104857.6. Just do this division, that is the answer. It will be 38 point something, I guess. Is it?
8.1. So we'll take a higher number, no?
Yeah, so we'll take 39, okay. Since these are unspanned, okay, so you cannot have like fraction of a block, you have to take a whole block. So the moment it exceeds 38, we'll take 39 blocks. So that is your answer.
Okay. Total blocks. This is one block is 104857.
Yeah, one block is storing this much memory, this much bytes, this many bytes, 104857.6 bytes. That is the capacity of one block.
And we are having
We are having
100,
4 into 10 to the power 5, this many bytes. So how many blocks will
10,000
need? Just divide.
10,000 blocks we are having.
Yeah.
What about index memory, madam?
Index memory.
That each index
This
entry.
is your total. This is the each index entry. See, 40 bytes, 30 plus 10. Here it is given 30 bytes and pointer field is 10 bytes.
Okay,
So
this
this
40
oh,
bytes
sorry, sorry.
memory is also to be included, no?
Sorry.
This 40 bytes memory is also to be added.
So that's what I did. Total entries is 40 into 10 to the power 4. See? So 4 into 10 to the power 5 I've written here.
What is this 10, 10 to the power of 4 is your total number of blocks.
Yeah, see,
So
I'll
each
just break
blocks
it
is
down.
40 bytes. So we are
Look,
having
how many blocks do we have that we need to point to? 10 to the power 4 blocks. So
10
each entry is going to point to 10 to the power, each entry is going to point to one block. So we need 10 to the power 4 such entries.
Okay, and each
So 40 into 10 to the power 4.
okay, yeah, yeah,
That is the
40.
total memory for index.
Okay,
Now you
okay,
have to divide that into blocks, and each block stores this much. So just divide it and you'll get the number of blocks.
yes, yes, okay, okay. Thank you very much. We can move to
No
the next.
problem. Yeah, okay. Okay, so this is number 4. Now see, there's a common information here. There's a multi-level index with 4 levels, L1 and 2, L3 and L4. L1 is the innermost. This is a multi-level index, like I showed you, innermost, then L4 is the outermost. That is, we're forming indexes on top of indexes. So let the index blocking factor or the maximum number, index blocking factor is nothing, it's the maximum number of entries held by a block. Okay, so one block can have 50 index entries. So this is your information. Now you have to find if the number of blocks in level 1 is 100,000, then how many blocks are required at level 2, 3 and 4? Just compute this and tell me the answer.
Yeah, that what is 100,000 divided by 50 will give 40.
It'll give you 2,000.
2,000 by 50 will give 40, and
And 40 by 50, we need at least one block, so we'll
minimum
take this.
so one block. So that will be the answer.
So this is the answer. Is this clear for everyone? Okay, then I'll move to the next one. Okay, see this. This is very important. This type of questions you'll get. Given the multi-level access structure, the number of block accesses required to read a record. See, I want to read a record from the disk. How many block accesses do I need? I have 4 levels of indexes.
So, up to leaf level, you will get 4. And this is
Yeah.
B plus or B tree, madam, because there is a difference, no?
This is just consider it a normal multi-level index. You don't have to go into data structures. Just think of
Okay.
it as indexes.
Ma'am, I think five, four for
Five.
block and one for record.
One for
Four,
record.
yes, 4 blocks for the index entries and one for the disk pointer. So we have to end total 5 block accesses.
Can you explain this?
See, there are 4 levels of indexes: L1, L2, L3, L4, right?
Yes.
So wait, see. So this is the outermost index L4. Then from here we have another index L3. Like this, we'll have up to L1. Now from L1, we'll only have record pointers to the disk. So here you'll get one block access. You first have to access index level 4, then another block access at level 3, another at level 2, another at level 1. So you'll totally have 4 block accesses for the indexes only. Then you'll have one more for the disk. So plus one. So total you'll have 5 block accesses.
Okay.
Okay. Okay. So the next question is, consider a B tree. Now this one I want you people to solve. Okay. This I will discuss in the next session only. You have to solve this by yourself.
No, yesterday we tried, we could not do with Tusharji, and he
Okay.
was suggesting new madam will come, you can ask her.
Okay, okay, okay. Okay,
Yeah.
fine. I'll solve this.
Yeah, thank you.
So here it is given. Okay, let me copy this. Okay, since I don't have much time, I can just show you here. Okay, I did a solution file for this. Just let me find that.
After your, we are closing the session by 8 or before that?
8.
Okay, after this, what is that we are planning?
After this, we'll take another session on Saturday. There we will complete this and start week 10.
Okay, okay. No, today's session after the practice assignment, you are going to discuss something?
After
Nothing.
the practice assignment, if I have time, I will discuss a little bit of hashing.
Okay, go ahead, madam. Thank you.
Okay, let me just find that file. Yeah, here. Okay. So I did the solution here. I'll just explain from here. Okay.
Yes.
So on an average, what is given here? The B tree based index with order P19, right? So assume each node of B tree is 73% full. So if the height is 3, then what is the maximum number of keys that can be accommodated? See, here on an average, each node will have 73% full, right? So we'll do 0.73 into the order. Okay. So that will give approximately 14 tree pointers. Remember, this is pointers. I'm not talking about search keys. This is pointers.
Sir, how,
Okay.
ma'am, how we know this pointers, not keys? How we
See from here, when you're saying that 73% full, na, it means that in this question, okay, yeah, this could be given actually. We could give this that here full means that we're talking about child pointers. This is not search key values, but it is very close. The values are very close actually. So if you take 73% of 19, you'll get approximately 14 tree pointers. And so on an average, each node will have, see, n minus 1, that is 13 keys.
No, but we can
Okay.
also 13 also, no,
If
approximately,
you do that, if you, no, no, this will
because
approximately, the value will come
73%,
40.
no, it is coming 73.87. So as a whole number, we have to take, no, number of keys cannot be point,
How much is it coming? 0.73 into 19?
0.87, 13.87.
So you have to take 14 only. You have to
No,
take a whole number now, because like I said, you, the moment it exceeds 13, you have to take the next whole number.
no, that is for the number of blocks. Here it says each node will have, okay, being 73% is minimum.
Yeah.
Uh, so it can have more also. How is that? How to read that? Full, 73% full.
Yeah, it is 73% full. Like there is still 27% left.
But if you take 14, it is more than 73%.
That's okay. You don't have to be that specific. Just take the approximate value. So it is written here, approximately 14 pointers.
Yeah, that is a solution they've given. But in the question, it says 73% full.
Yeah.
Full, it should not cross 73%, correct? No? Or
So
it
that
is a
means
wrong.
we have to specify in the question then. Okay. I'll discuss
Yeah,
this.
yeah, please. If it is 73% means it should not cross 73.
Okay. I'll discuss that
But
part,
when
but
we take
let me tell you
14,
the.
yeah, yeah. When we take 14, it is more than 73. Okay, that is one point, madam. You can go ahead next.
Okay, I'll discuss that, but let me tell you the concept behind this. Okay.
Please, please,
So
please.
we have approximately 14 tree pointers. That means 13 keys. This is clear, right?
Okay, 13. Okay, 13 keys. So
13
pointers
keys.
are 14.
Yeah, 14 pointers and 13 keys.
Okay, 13 keys. Okay.
So in level 0, okay, in level 0, we'll
ma'am, in
have.
this type of questions, more data is
Yeah,
needed in
yeah,
the.
yeah. Okay, I'll
Okay.
talk about that. We'll discuss that. And we'll probably update this question.
So 13 keys in level 0.
Yeah. So 13 keys in level 0. But there is one node only, right? So number of keys is 13 and number of child pointers is 14. Now in level 1, how many nodes will have? We have 14 child pointers, so obviously 14 nodes will have. And in
Yes.
each node we have 13 keys, so total number of keys is 182. And total number of pointers, again maximum, is 14 into 14, 196. Like this you can extend till level 3, and
Oh,
then you
okay.
have to add the sum of every level, the total number of keys, that will be this 13 plus 182 plus 2548 plus 35,672.
So
So
yesterday
this will be the
we,
answer.
yeah, yesterday we did not have any idea of pointers at all because here pointers was not given. We were multiplying 14 into 13 into 13 into 13.
No. Obviously, yeah, you can't do this sum without the idea of pointers.
Okay, so the number of
But I
pointers,
will I will discuss this 73% full. We have to probably put
yeah.
some more
So
info.
even in the question there, it is not given. There is not any.
Yeah,
It
we'll
says
give if
only
you
the
need to
number of
take
keys.
the seal value or the floor value.
No, that is one thing, madam. In this question, question number 6 itself, uh,
Hmm.
how we are supposed to know that we have to take pointers because assume each node of B tree is 73%, height of the tree is 3. What is the maximum number of keys?
Hmm.
Keys means number of At what is the number of keys? Keys of the our database, isn't it?
Yeah, each key, like the keys in the nodes, keys present in the nodes at each level. So number
Okay.
of keys that can be accommodated in the tree. That is, you have to take the sum of all the
In
keys that are
level
present
one,
in each
in
level.
level one, there are 182 keys.
Yeah, yeah,
Okay. So, and number of child nodes will be 14.
yes. See,
So,
in the previous level you have 14 pointers, so obviously 14 child nodes in this level, the next level.
yeah, for each child node, you can have another four.
Now each
Uh,
child node can have at max 14 pointers again. So 14 into 14, 196.
no, but this is 19 p equal
But
to
each of the nodes are 73% full. So you can't take 19.
so you have to take 14.
Yeah, since all of them are 73% full, none of them are like 100% full.
Yeah,
See,
no,
each node
if
is
we can
73.
draw it in the sense, first you will have root node, then below that you will have 14 child nodes.
Yeah. Then
Each child
again,
node
each child node will have again 14 child nodes.
14, and
Yeah.
14 into 14 only you have to take. Yes, 13 we should
Yeah.
forget it.
So
Okay,
as the levels increase, you have to keep on multiplying by 14 for each
it's basically
child
14
node.
cube plus 1,
14 to the power 4.
4.
Uh,
14 to the power of 4 plus
yeah.
1 plus 4. That last one, 13, will be there for the root node because
Which one?
1
Sorry.
less. No, it is not. It is 14 to the power of 4 minus 1.
Y minus 1?
That number of keys, no? I mean, zero level, it will be only 13.
No, no, you can't do it like that. Now you have to do the number of keys for each node. You can't do 14 to the power 4 minus 1.
Okay, okay. Correct, correct, correct. Okay.
You
14
have to
into
check
4.
for each node.
Okay. And I understood, madam. Understood, understood.
Okay.
Thank you.
So you understood the concept now. I will discuss about the information here.
Yeah, yeah. Concept, I got the concept now.
Okay,
Thank you, thank
great.
you.
Okay, so next, so this will be the answer 38 for 415. Okay.
Yes, yes,
So
correct.
consider a B tree of order 3. If you have 9 elements to be inserted, what will be the maximum number of splits? Now this is a very good question. Uh, I'll draw this tree. B tree of order 3. Okay. See. So I have to insert 9 elements, right? So let me take the elements as 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just taking an example. These are 9 elements I have to insert. So remember in B tree there are no duplicates.
Madam,
Okay.
madam, if
Yes.
you take this example only, you will get the maximum. Otherwise,
Yeah,
you will
we
not get
need we
maximum.
need the maximum splits. That is the concept here. When will the
Yeah, yeah.
maximum
No, no,
splits
you
happen?
just like that we are taking. No, you told.
Yeah, I was going to say that at the end, but
If you don't take
yeah,
ascending order, you will not get the maximum.
yeah, that's great. Yeah, you understand that. That's great. So here we will. You need me to make the tree, or you want to make it by yourselves?
No, for
No,
others,
ma'am,
I
please
have
make that
completed
one.
this, but for others, you
Okay,
can.
okay,
It's
okay.
being
I'll make it.
recorded. I did
I'll,
not see it was recorded. So
no, no.
you.
All of you need me to do make the tree or not?
Ma'am, I want to make the tree because I got the 4 split but not 5. The
Okay,
answer is
okay.
5, I think.
I'll make it. I'll make it. Okay. So first we'll enter 1, right? What is the order? 3, right?
Yes, ma'am.
Okay. So we can have maximum 2 key values. Next we'll have 1 and 2. So these two are entered. Next I want to enter 3. So I'll split here. I want to enter 3. So I'll split this node. It will go here. To the left I have 1. And here I have 3. Okay. Next I want 4. I can directly insert here. Next I want 5. Again I'll split. 4 will go up to the root. Okay, so this becomes 2, 4. To the left you'll have 1. Here 3 will come, and to the rightmost we'll have 5. Next I want to insert 6. I can insert directly 6 here. Next I want to insert 7. Okay. Okay, I want to insert 7. Again I'll split this node, it will go up here. So I'll show you the intermediate step here, okay? So here we'll have 1, 3, and the 6 we will take from here. Okay, let me just draw the final structure, that will be easier. This will be confusing.
For this, we take the two split for the root node.
Yeah,
Oh,
here one split, here one split. That is why you're getting 4, na? You have
yes,
to take
yes.
both the splits. So we'll insert, after doing the split, we'll get 4 as the root node. To the left side, we'll have 2. Right, we'll have,
6.
uh, hold on. 6, yeah, 6 we'll have. Then here we'll have 5, 7, 1, 3. Okay, next we can enter 8 here. Now again, if we want to enter 9, we have to split. Okay, so 8 will go above. So the final structure becomes 4. This is 2. This is 6. Now 8 is greater than 6, so to the right hand side. This is 1. This is 3, 5, 7. Now finally we want to enter 9. I'm sorry, did I make a mistake here? Okay, no.
7 and
9
9
will
will
be
come.
9 will be here.
Madam, 7, 8
No,
when it goes up, 7 and 9 can come together, no?
now how will it come together? No, 7 has to be on the left side of 8 and 9 has to be on the right side of 8.
Okay,
7 is
3.
less.
Yeah, yeah, correct. 3
Okay, so
pointers.
this is the final answer. So how many splits we are getting? We're getting one split here, two splits here. So this is 2 here, one more 3, here one more 4, and this one 5. So 5 splits. Okay, that's your answer. Okay, so
Okay,
this
madam.
is,
Ma'am, can you go back
yeah, sure. Yeah,
and explain the last, like when you add 8,
8.
then 9, I guess.
Okay, 9. See, 9 I am entering here, no? This node I have to enter
Yes.
9. So this node is already full. So I have to make a split. So I'll split with the middle element. This will go up to its parent node, that is A6, this one.
6. Okay, okay.
But 8 is greater than 6, so it will come to the right side, like here. But now you get two separate nodes, one for 7, one for 9. And 7 is less than 8, so it will come to the left hand side, and 9 is greater, so it will come to the right hand side.
Got it.
Okay.
Okay, sharp 8 o'clock you have completed. So still is there, no? One more. Okay.
No, there are more questions actually. There are 11. There are a lot of questions, but I'll discuss. This will be the last one, okay, for today. Next ones I'll discuss in the next session. Or if there is any specific question among these that you want me to discuss, you can tell me.
Ma'am, there is one question in the grading for hashing which we don't have any idea. Please give some hint.
Okay. What is the concept on?
Ma'am, I will give the
Is it
question
on,
again.
okay, is it on dynamic hashing or is it on
I think
static
it's
hashing?
dynamic hashing.
Hi, Greta Nasta.
Actually, we cannot discuss this graded assignment questions until you have submitted it. So for now you can go through the lectures. There is not much to discuss in hashing really. The lectures are pretty much exhaustive. They
No,
have
the
covered
particular
everything.
question what she is asking, the professor has discussed it, madam.
Yeah, yeah.
Lectures.
Okay, okay, then I'll again watch.
Yeah.
Just watch the week 4 lectures, okay? That covers hashing. I'm sorry, week 9, 9.4, lecture number
Thank
9.4. Just
Okay,
watch that, and if you have any queries, I'll solve it in the next session.
okay, ma'am.
So, any question from here that you want me to solve in this practice assignment?
No, ma'am, we did it yesterday.
Okay, good then. Okay, so I'll wrap it up here, and I will finish week 9 in the next session, and we'll start week 10 on Saturday. And
Okay,
I'll get
thank
back to
you.
you with those queries that you had on height and that question. I'll see if we can
Again.
add more info to it.
Sure, sure.
Okay, thank you so much.
Thank you, Manideepa. Bye.
Uh,
Good night.
okay.